Morning, this is Ms. Billerbeck, and we are going to talk about modeling with quadratic functions. So first, let's talk about a vertical motion model. This is essential for physics and engineering. We use gravitational acceleration, which in English units is negative 32 feet per second squared, or negative 9.8 meters per second squared. So when we talk about the vertical motion model, we're going to use h of t for the object height, and h naught, 0 in England is pronounced as naught apparently, so it's h naught equals the initial height, or h sub 0, you might hear it referred to that. V naught, or v sub 0, equals the initial velocity, and t is time in seconds. So our English unit equation for vertical motion will be h of t equals negative 16t squared plus v naught t plus h naught. So the reason why this is negative 16 and not negative 32 is there's a 1/2 times acceleration. So the half times this, half of this acceleration is negative 16. And half of this acceleration would be negative 4.9 t squared plus v naught t plus h naught. So that would be the metric equation for this. So this book, you'll mostly be using the English units, but in engineering, you tend to use the metric unit. So I wanted to make sure you were aware of both equations. All right, so first let's dabble with this pool deck and trying to create a quadratic formula. So the first pool deck we see is we have 2x for our length, and x is going to be our width. So if we're going to say area of a rectangle equals length times width, and we have our width equals x, but then we have these parts right here, 4 and 4. So it's going to be x plus 4 plus 4 for the width, and the length will be 2x. And then we have the 4 here and the 4 right here. So that'll be plus 4 plus 4. So our width is going to be x plus 8, and our length is going to be 2x plus 8. All right, so now let's put this in a formula for area. So let's make this a function of x. So we're going to go write a of x equals, and then our length is 2x plus 8, and our width will be x plus 8. So we can FOIL this and have a simplified equation of, so first would be 2x squared, outer would be plus 16x, inner plus 8x, and last plus 64. So our final equation for area will be 2x squared plus, and that gives us 24x plus 64, and this is in feet squared. So we should, actually, I did not say units. So if we don't say units, then we can't assume they're going to be feet. So we would say that this is going to be units squared, or little u squared, like that stands for units squared. Okay, so how does it change if the length is 3 times the width. So instead of this being 2 times the width, it's 3 times the width. Okay, so then we have the length is 3x plus 8, because we have the 4 here and the 4 here, and the width doesn't change. It's just x plus that 4 and that 4, so 8. Okay, so we have a, let's call this a sub 3 of x for the 3 times the width. Okay, so it's different than this a of x. This subscript is just a name. It doesn't do anything mathematically except represent a different area. So then we have 3x plus 8 and x plus 8. So we're going to FOIL this. We get 3x squared plus 24x plus 8x plus 64. So our final area for this will be 3x squared. And then this becomes plus 32x and then plus 64. So when we and this will be units, I'll spell it out this time since I have some room, units squared. Okay, so if we look at the 2, we just see the coefficient is different. So this has a greater vertical stretch than this one. But the y-intercept, surprisingly, is the same. Okay, so it just looks like the vertical stretch is different. We've got a little change here with the middle term. But that's basically, it's just more of a vertical stretch, as this is stretched this way. So it would show a bit of a stretch in the pool and a stretch in the equation. So there you go. All right, so let's do something near and dear to my heart, is diving. I used to love being a diver in high school. And I started a diving team at one of the high schools I taught at. So a diver jumps off a platform at an initial velocity of 8 feet per second. So write the vertical motion model to represent this quadratic function if the diving platform is 20 feet high. All right, so we have velocity is 8, so we're given velocity and its initial velocity, so that's v naught, is 8 feet per second. We know our acceleration then is going to be that negative 32 feet per second squared, because we're using English units. And then we have the initial height is, so h naught is 20 feet. Okay, so let's write the vertical motion equation. So we have h of t equals, and then we have negative 16, which is half the negative 32. So negative 16t squared plus our v naught we have is 8 feet per second times t. And then we have h naught at 20 feet. So that was easy. All right, so we have a beautiful quadratic equation in standard form. So we can find our maximum height by finding the axis of symmetry. So that would be this formula, negative b over 2a. So we have a is here, b is here, and c is here. So this is going to be negative 8, which is b, over 2 times negative 16. So this becomes, there's 2 negatives, so we have a positive. We have 8 over 32, which is 1/4. All right, so we know in 1/4 of a second, she's at her maximum height. So what is that height? So let's see. We're going to go find h of 1/4 to find the maximum height, because we know she's diving in a parabola that is upside down or opening downward because of that -a. So we have -16 times 1/4 squared plus 8 times 1/4, and then plus 20. So this becomes 1/16 times 16, -16, which is just -1. This 8 times 1/4 is 2. And then we have plus 20. So we have a maximum height here of 21 feet. Okay, so there you have it. It's always lovely to revisit diving. It's a beautiful parabola that they make when they jump off the boards. All right, so example 3, we're going to make a scatter plot of the data and graph the function f of x equals -8x squared plus 9x plus 745. So make a residual plot and describe the curve fit of the data. So use a quadratic regression. Okay, so we're going to do this in 2 different ways. Okay, so we'll use I'll show you how to do that on Desmos, and we also do it manually. So what is the predicted revenue in the 5th and 6th increases? Oh, and we'll also use the graphing calculator. All right, so let's take a look at the model. Okay, so I put some data together already to make it a little easier to see. All right, so let's plot a few of these points. So our current scatter plot is 0, 730. So right here, here's 700, so 730 is right about here. And then 1, 850, which is right about here. 2 is 930, so that's 900, which is right about here. 3 is 951. It's right about here. You can see it's kind of leveling off. And then 4 is 1010. So we can see this is just kind of, it's a little curved, but it is modeling. Could it be modeled by a line, or it could be modeled by a parabola? So if we assume that it is a parabola, let's take a look at the equation we have here. I should write that down, is f of x equals -8x squared plus 95x, and then plus 745. So let's graph that one pretty quickly, and we'll take a look at the residuals. All right, so at 0, we're at 745. So that's right about right here. So there's just a tad bit of a difference there. At 1, we're at 832. So that's just a little under. At 2, we're at 903. So we're really close right here to 900. And at 3, we are at 958. So these two are almost the identical ones here. And at 4, we're at 997. So we're again almost right there. So that makes a much better curve. So that looks like a really nice curve fit. So if we analyze those 2 points, and we find the residual, we see we have a residual of -15 here. 850 minus 832 is positive 18, and 930 minus 903 is 27. Then we have 951 minus 958 is a -7, and 1010 minus 997 is positive 13. So let's go ahead and graph these points and see, is this a good curve fit of the pink scatter plot with this actual equation here? So all right, so at 0, we have a -15. 0, we're at -15, so that's 14. -15 is right here for our residual. At 1, we were at 18, which is right here. At 2, we're at 27. That's way off this page, sorry. And then at 3, we're at -7. So that's 6, so -7's right here. And then at 4, we are at 13. So 13, that's 14, so 13's right about here. So when we look at this residual plot, they're just all over the place. So if we have chaos on our residual plot, that's a good thing. So that means that this is probably a really good curve fit because there's no pattern to the residual plot. So that means that we've got a few points on each side of our curve. All right, so let's go to Desmos now and let's analyze this problem that we have. And we can kind of predict what we're going to have in the 5th and 6th increases. All right, let me share that screen. Okay, here we go. So we've got, this is our original data right here. And we have the equation here that we were given for our residual plot. So we can see a few of the scatter plot points here. And then if we enter the equations with y sub 1 tilde negative x sub 1 squared plus 95x sub 1, then it pops up all this data with the R values. So this is a pretty strong R value, 9.68. But let's take a look at some of these other R values. So far that's a pretty high one. Here's a linear model. And if we look at the R value here, it's 0.96. So that's a little less than the 0.968. So this 0.965, it's close. Remember, it looked kind of linear, but it's closer to a parabola. And this is 0.982. So just that generic curve fitting didn't work as well as that actual formula we were given. So the actual formula we were given, this one, is much closer curve fit than what the computer came up with, which is very surprising. Oh wait, it's 0.98. And this one's 0.968. So actually the computer came up with an even better equation for that parabola at -12.9 for the A, and then the B instead of 95 at 117.8, and then the C was 736. So that's kind of interesting. The curve fitting is very good using the graphing calculators. And then we look at the exponential. Well, that's 0.91. So it really doesn't fit the exponential. So let's look at, they all look very good, right in here. You know, they're all looking really good in this region. So that's why it was just a great fit. Okay, but let's look at this top data up here. Okay, so we see that the exponential is just going off to infinity here. It's the red line. And we see our curve is coming around here. So right about at 6, so right about 6, that's the vertex. So if we predict, you know, at 6, it's going to be about 1,027. It's going to go down a bit because that's not quite 6 yet. So it's going to, that's the maximum at 5.9. So 6, it'll be a little less than 1,027. So maybe it'll be closer to 1,010 as the other point was. So, and then at 5, let's take a look at the graphing calculator for that one. Again, the graphing calculator is it's much easier to use for this. All right, so let's take a look at the graphing calculator. So when we start the graphing calculator, we hit the y equals button, and then we can put in our equation here. Now I've already gone to this table set, hitting second table set. So I started at table value of 0. So and with a change in table value of 1. So I don't want any decimals. I just want to do 0, 1, 2, etc. So now I'm going to go to the table, and this is what I see. So this is the f of x, the function in here. So we can see, well, at 5, it's at 1,020. And at 6, the predicted value would be 1,027. So we did see that at 5.9, it was about 1,027. So that's pretty good. And then let's look at 7. See what 7, it should start going down. Yep, it's going down again. So around 7, it's 1,018. So right around that vertex, those values should be very similar, like 1,020 and 1,018. So there you go. That's one way to find your vertex when it goes up, 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 and then all of a sudden it's going down. You know that the maximum point was pretty close to your vertex, and that's when you would start using decimals right around the 6 values. So that way you can save some time. All right, that's it for this lesson. Have a wonderful day.